With splash erosion, splash material falling back onto the soil surface generates a layer of loose material sitting on top of the original soil. Drop impacts must lift this loose material before detaching particles from the cohesive soil surface. As a result, loose material provides a degree of protection against detachment. The effect of protection by the loose material sitting on the surface is taken into account in this equation. H is the degree of protection provided by the loose material. Md is the mass detached from the soil surface when there is no loose material. Ml is the mass of loose material splashed when loose material completely protects the underlying soil surface. As time goes by, H increases over the surface, particularly in the downstroke direction. Drop impacts also break down soil aggregates and hammer the soil surface, leading to soil crusts developing. The crusting of the soil surface affects Md. Generally, the values of H, Md and Ml are not known in experiments on splash erosion. With raindrop-induced siltation, like splash erosion, detached particles fall back onto the soil surface and wait before moving again. Consequently, we have an equation similar to the one shown for splash erosion. In this case, Mu is the mass lifted into the flow, H is the degree of protection provided by the loose material, Md is the mass detached from the soil surface when there is no loose material, Ml is the mass of loose particles lifted into the flow when loose material completely protects the underlying surface. As time goes by, H tends to increase over the surface, particularly in the downstroke direction. Generally, the values of H, Md and Ml are unknown in experiments with rain-impacted flow. The development of the loose layer depends on soil properties. Generally, the loose layer is more prominent with sandy and well-aggregated soils. When raindrop-induced siltation is followed by flow-driven siltation, material of the affected size lifted in the flow-driven siltation zone or entering the zone from upslope is discharged across the boundary without further effective drop impact. Other particles of different size and density will still travel over the downstream boundary by raindrop-induced siltation and produce a layer of loose material in the flow-driven siltation zone. However, the value of H in that zone will be reduced as a result of the winnowing of particles moving out of that zone by flow-driven siltation. When this simple model was applied to simulating raindrop-induced siltation followed by flow-driven siltation, the transition from raindrop-induced siltation to flow-driven siltation in transporting coal over the downstream boundary was marked by changes in the discharge rates of the other material because of the reduction of H in the area where flow-driven siltation occurred. Temporal patterns of soil loss rate for any given soil can vary markedly when rainfall intensity is varied during an experiment, as shown by the red line in these three graphs. Why these patterns occur was subject to considerable speculation by the authors of the paper. Here is another set of experiments where variations in rainfall intensity made considerable changes to the temporal patterns of soil loss. Why these patterns occurred again was subject to considerable speculation by the authors of the paper. Basically, the physical and chemical properties of the soil have a great influence on the response to the detachment and transport mechanisms that operate on the eroding surface. Soil surfaces are not benign during a rainfall event. Changes will occur on the soil surface which cause the sediment discharge to vary with time when rainfall intensity is held constant. Apart from monitoring temporal variations in sediment discharge, data on the size and densities of the particle discharge warrants correction. Data on the critical shear stress associated with flow detachment would be useful in identifying when flow detachment occurs. Data on the temporal and spatial variation in flow depth and velocity warrant collection, but difficult to do in rain-impacted flows. Visual observation of dye travel does not produce accurate results, as the dye front is dispersed by the impacting raindrops. The notion that rain has a certain ability to cause erosion when soils have a certain innate ability to resist erosion that underpins the concept of rainfall erosibility and soil erodibility does not apply to rain-impacted flows that operate in sheet and inter-erosion areas.